All right. Sorry about that. You can see it now? Can you hear me?
Yes.
Can you see the screen?
Yes.
Okay. All right. So today I want to talk about what I'll call what is called the W12 path space of a smooth manifold, finite dimensional smooth manifold, the energy functional, and these paths are denoted omega 1, 2 of M, and we're going to consider paths that start at P and end at Q, so we'll use that notation. The energy functional, which symbolically is written well, maybe I'll write it this way. Okay, so we have to make sense of all of that. And I want to prove that in this context, the critical points, so the first theorem is that the critical points of E are C infinity curves, and they're geodesics in the classic sense. And they're smooth geodesics, even though they lie in a space of much rougher paths. And the second theorem is that condition C, the Palais-Smale condition C that I talked about last time, holds for this energy functional. So you can do Morse theory on this Hilbert manifold of rough paths. Okay, so that's the plan for today. The computations that show that critical points actually have enough smoothness to prove their geodesics in the classic sense, and the similar computation that shows that condition C holds are typical sorts of manipulations in these spaces of these Hilbert spaces of functions with some sort of rough control. And it's always a question of using your rough control to get better control. And those arguments can be somewhat complicated and intricate. So I'm not going to go through the details by any means of all of them, but I'll try to point out to you the main points or high points of those more technical analytic arguments. But I'm going to start very gently, because I know when I first started learning about these Sobolev type spaces and so on, I was very confused about what these objects really were and what these norms meant and keeping all the norms straight. So let me just spend a few minutes talking about all of that at a very elementary level for W12, which is the main norm of interest here. So let's think about functions from the interval 0, 1, I is always 0, 1, to the real numbers. There's a notion that such a function is absolutely continuous. Which I'll remind you from real analysis. So you can say continuity this way. So continuity you can formulate this way. For all epsilon greater than 0, there exists a delta greater than 0, such that if J in I is an interval, say from P to Q, with the length of J less than delta, then the difference at the endpoints is less than epsilon. This is the reformulation, slight reformulation, of the completely standard epsilon delta notion of continuity. So absolute continuity is a generalization of this. It says anytime you have a disjoint union of a finite number of intervals with the total length less than delta, and let's say Ji is the interval Pi, Qi, then the sum of the difference at the endpoints is less than epsilon. Okay. So no matter how many intervals you have, they have to be only finitely many, as long as their total length is at most delta, then the difference at the endpoints, absolute value added up, is at most epsilon. So that's the standard definition of absolute continuity. And then there's a theorem in real analysis that says that F is absolutely continuous if and only if there exists a measurable function G, measurable and integrable function G, such that F of t is F of 0 plus the integral from 0 to t of G of S ds. Okay. That's a basic real analysis theorem. This G in general is only measurable and of course integrable. G is called the derivative F prime. And in fact, G actually has well-defined value. I mean, F prime actually exists in the naive sense of limits almost everywhere. But of course, it's not going to be continuous or anything like that. But this is what you mean by the derivative of an absolutely continuous function. It's this measurable function G that integrates up to give F. So we say that F mapping the interval to R is in W1, 2, so this is a space of functions. W1, 2 maps with the interval into R if F is absolutely continuous and F prime is in L2. So this measurable function, which a priori is only in FL1, is required to be square integrable, not just integrable. So that's an extra condition. And so the notation comes from the one is the first number is the number of derivatives that you're considering. And the second number is the LP space in which you're working. So these are functions said to have one derivative in L2, okay, which implies that they are absolutely continuous. Okay. Now, functions in L2 aren't really functions. They're measurable functions that are square integrable. So you can vary the values of an L2 function on any set of measure 0, and that you have the same function. And of course, one way to think about L2 functions is to take Cauchy sequences of C infinity functions where the norm is the L2 norm. And then every Cauchy sequence will have a limit in L2, which won't be a smooth function, won't even necessarily be a continuous function. Typical, I mean, a very simple example of a L2 function would be a function like this, constant on various intervals. So if this is 0 and this is 1, that would be an L2 function. Now you might say, well, what value are you giving at the endpoints of these intervals? In fact, it doesn't matter what value you give at the endpoints. You can pick either one of these values or any other value for that matter, because changing the value of the function at a finite set, as we would be doing here, doesn't change the function as an L2 function. Its equivalence classes of measurable functions up to being equal off a set of measure 0. Okay, so that's a W12, one derivative in L2. We're going to be considering the space of W12 functions of the interval into Rn. Finite dimensional Rn is defined exactly the same way. You can say f is here if and only if the n coordinate functions of f are in W12 of R. Or you can say, we can define the W12 inner product of two functions like this. It's simply the usual inner product of where they start plus the integral from 0 to 1 of f prime of t, g prime of t. That should be, if I'm working in Rn, inner product in Rn dt. Okay. This is a positive definite inner product. And W12 of Rn, I and Rn is complete with respect to this metric that this inner product defines. Let me just say a word about that. Suppose you have a sequence, a Cauchy sequence. For this W12 norm. Okay. Well, the first thing you see is that Fn of 0 is a Cauchy sequence in Rn, because the norm square, the W12 norm, is the norm of F0 squared plus the integral of F prime squared dt. So if the norms form a Cauchy sequence, the norms of the values at F0 form a Cauchy sequence. So they converge. So the Fn of 0 converge to what we'll call F of 0. And the next thing you need is you need uniform continuity on the Fn so that you can take a limit. Okay. So we have uniform continuity. Because if you have a function in W12 and two values A and B in the real numbers, the difference between A and B is less than or equal to the square root of the difference between A and B times the norm of F. Times the norm of F, W12. Okay. And that's Cauchy-Schwarz. If you take the length of F restricted to AB, assuming A here is less than B, well, that's just the integral from A to B of the norm of the derivative. So I want to apply Cauchy-Schwarz to the first function being the norm of the derivative and the second function being 1. So Cauchy-Schwarz says the integral from a to b of the inner product of these two functions, dt, is less than or equal to the integral from a to b of the norm square, it's the same norm, of f dt square root times the integral from a to b of 1 dt square root. So this is the L2 norm of f, and this is the square root of b minus a. So, but the L2 norm of f prime, but the L2 norm of f prime is part of the W12 norm of f. So the L2 norm of f prime is less than or equal to the W12 norm. So you see, here's a uniform continuity. So now it's easy, and it's a standard argument. If you have an equicontinuity, if you have a sequence of functions which are converging at the origin and they're equicontinuous, then they converge uniformly to a limit, and the uniform convergence, the limit is in W12. In fact, what this argument is really proving is that the map from W12 of W12 functions on the interval into continuous functions on the interval, first of all, is bounded, continuous, but it sends bounded sets to precompact sets. So if you have a sequence, a bounded sequence here, and you push it into C naught, you can extract a limit in C naught of that bounded sequence, of the image of that bounded sequence. Precompact just means the closure is compact. Okay. So that's a little introduction into W12. So W12 of the maps of the interval into Rn is a Hilbert space, complete metric space where the inner product of f and g is f0, g0, usual Euclidean inner product, plus the integral from 0 to 1 of f prime of t, g prime of t, dt. And to know, I mean, it's the same argument that I just gave a minute ago, to know that this integral actually exists, you bound this integral by the product of the L2 norms of the two factors, and the L2 norms are less than or equal to the W12 norms. So since these have finite norms, this integral is well defined. Okay, so that's the Hilbert space. Now, there are two ways to get from this linear situation to the nonlinear situation of paths in a smooth manifold. One is to require conditions of that like this locally in coordinate patches and define the norm by patching together the norms with respect to coordinate patches by some partition of unity. And that all works, and that's in fact a good way to do it. But I want to take a more naive and simpler approach. So I'm going to suppose I have a smooth manifold properly embedded in Euclidean space. So it may be a non-compact manifold, but if it is, the ends of the manifold go off to infinity in Rn. So it's properly embedded. So it's in particular a closed subset. And every point in Euclidean, in the ambient Euclidean space, has a neighborhood, so that this looks like M looks like a coordinate subspace locally on usual conditions. Okay. So now I can define 1, 2 paths on M, let's say because all I'll be interested in is paths starting in P and ending in Q. That's going to be a subspace of W12 of maps of the interval into Rn. And it's exactly the space you would imagine. It's the gamma in W12 I Rn with the following properties. Well, gamma of 0 is P, gamma of 1 is Q. So these paths start at P and end at Q, and gamma T is in M for all T in the interval. So these are simply paths in M that go from P to Q, which when considered as paths in Euclidean space are in W12. Is that a question? No. All right. Okay. So the first lemma. So we have to see what sort of subset this is. So the claim is that in fact it's a closed subset, which is a smooth submanifold. So the first lemma is that this thing is a closed subset. Okay. Now here we have to be a little careful because there's two notions. I mean, usually you would write subspace, and the trouble is, since this is a vector, there's an infinite dimensional vector space, there's really, you use the word closed subspace in two different ways. One way means a linear subspace, which is closed, and the other just means in the topology, it's a closed subset. So here, this is not a linear subspace. I just mean as this Hilbert space has a topology induced by the metric, and in that topology, this is a topologically closed subset. And the proof is the absolute convergence I was just talking about, convergence, absolute convergence in C0 that I was just talking about. So if you have a sequence of paths in omega 1, 2, M, P, Q that converge to an element in W12, okay, then in fact, the gamma n converge uniformly to gamma. That is to say, a particular gamma n of T actually converges to gamma of T for all T in the interval. That's those computations I was just doing, comparing, because of the uniform continuity of these functions. Okay, well, the gamma n of T are in M. M is a closed subset of Euclidean space. That means that gamma of T is in M. That's for all T. And of course, gamma n of 0 is P for all n, implies gamma of 0 is P, and similarly for Q. So we end up, the limit is, because it's a limit in W12, is a W12 path in Euclidean space, but these conditions of being in the manifold starting at P and ending at Q follow from the strong convergence in C0, or actually follow from the convergence in C0. So this set of paths is a topologically closed subspace in this Hilbert space. Next, we want to see that it's a smooth manifold. Lemma omega 1, 2, M, P, Q in here is a smooth submanifold. So we want to find around every point. So here's the omega 1, 2, and here's a point gamma. We want to find a local patch here and a diffeomorphism to another patch that straightens out the phi, and this linear subspace, closed linear subspace, is supposed to be phi of gamma 1, 2, intersect u, if this is u, and this is v, okay? So they go to the origin. All right, so we need to find a diffeomorphism. Actually, we're going to construct it in this direction. That straightens out this curved subset and makes it just the closed linear subspace of the Hilbert space intersected a small ball. Okay. So the way I'm going to do that is I'm going to fix gamma in this subspace, and I'm going to define a map from W12 of Rn to W12 of Rn. Well, okay, so I forgot there's a step here before I do that. For this part of the argument only, I'm going to take a non-standard inner product in Euclidean space, but I'm just going to use that inner product to prove the smoothness result. Then I'm going to forget the inner product, and I'm going to use the standard inner product in Euclidean space from here on. And that's the inner product. The standard one is the one I use to define the norms. Okay. So let's pick an inner product. Pick a positive definite inner product on Rn that makes M totally geodesic. Okay. So you can always do that. You basically just straighten out the normal bundle of M in some metric, choose a metric, well, I won't say anything more. So you can find a metric on Euclidean space that makes M totally geodesic. And now using that metric, I'm going to define an exponential map. So I have the exponential map from NEP, which maps Rn to Rn. Exponential P at a vector V is the unique geodesic from P with tangent bundle, tangent vector V at time 1. Of course, for the standard inner product, these are straight lines. For a general inner product, you don't know that this exponential, well, I guess these are complete. So this exponential can be defined for all time. I'm going to use that now, and our gamma, so let's fix a gamma in omega 1, 2 of M, P, Q. And let's define the exponential at gamma of t as a map from W12 Rn into W12 I into Rn. So we send lambda of t, that's some W12 curve, goes to the curve exponential at gamma of t on lambda of t. So this is a one parameter family of points parameterized by t. This, in fact, it's easy to see, represents a W12 path in Rn just because the exponential is C infinity. Okay. And now let's call this map phi. It's easy to see that the differential of phi at the identity is the identity. So phi is a local diffeomorphism. And let's look at locally phi inverse of our subset W21 MPV. Well, this is exactly the lambda in W21 such that lambda of t is in the tangent space at gamma of t to m, and gamma of 0 equals gamma of 1 equals 1. Because m is totally geodesic, so for this exponential to land in m, for each t, gamma t has to be a tangent vector in the tangent space to m at gamma t. Furthermore, to end up with a path that starts at p and ends at q, gamma of 0 has to be 0 and gamma of 1 has to be 0. So this local diffeomorphism has the property that it does exactly what I wanted. It takes omega 1, 2 of MPQ near gamma, and it straightens it out to what I'm going to call omega 1, 2 MPQ tangent at gamma. So rather than writing capital T sub gamma of this space, I'm going to just put the gamma over here. And these are the set of curves in W1, 2 such that they lie in the tangent space and they vanish at the endpoints. Okay. So that's a linear subspace. Those are linear conditions. And it's easy to see that it's a closed subspace, just again, because the manifold is smoothly embedded. Absolute convergence under the norm. Okay. So omega 1, 2 MPQ gamma is a closed linear subspace. So it inherits an inner product, a positive definite inner product from the Hilbert space structure. And let's just say what it is. The W1, 2 norm of a pair of tangent vectors in gamma. So by this, I mean, these are tangent vectors. So these are vectors in this linear space. And I want to take the W1, 2 inner product restricted to this linear subspace, and I'll denote that inner product by sub gamma. So this is just the W1, 2 inner product restricted to this linear subspace. Well, what is it? It's supposed to be gamma of 0 inner product mu of 0, inner product in Euclidean space, plus the integral from 0 to 1 of gamma dot of t mu dot of t dt. Well, this is 0 because these tangent vectors start at the origin. So in fact, this inner product on this tangent space is simply the L2 norm of the derivatives, L2 inner product of the derivatives. And I'll denote the L2 inner product always by a sub-0. So this always means L2 inner product. Okay. All right, so let's summarize where we are now. So omega 1, 2, M, P, Q is a Hilbert submanifold, is a smooth submanifold of this Hilbert space. It's a smooth submanifold. The tangent space at any point gamma is denoted this way, and it's a closed subspace of this L2 of this W12 space, and the inner product in gamma of lambda mu is simply the L2 inner product of gamma dot and mu dot. Okay. So that's our space, that's our Hilbert, that's our Riemannian. So this is our Riemannian Hilbert manifold of paths that we're going to consider. These W12 paths in the manifold. Now you can ask questions about how intrinsic is this. Suppose I had a different isometric embedding of the manifold into Euclidean space. Well, it's pretty easy to see the Hilbert manifolds are diffeomorphic, but the Riemannian structures are very different, and it's not completely obvious how they're related. So in some sense, if you wanted to actually work with a Riemannian manifold M to begin with, it might be better to do this all intrinsically in terms of coordinate charts, but I'm not going to address that. For what we're interested in, these questions about the topology of the loop space, you're free to choose any smooth structure, any Riemannian metric, so you might as well take this thing to be a properly embedded smooth submanifold of Euclidean space with its induced metric. Okay. But I'm just pointing out there are more delicate things you might want to do. All right, now the energy functional. Well, we know what that is. The energy functional is a map from the space of paths into R. The energy of gamma is 1/2 the integral from 0 to 1 of gamma dot squared. And as before, a point I've made several times now, this integral is defined. Gamma dot is not a smooth function. It's not a continuous function. It's only an L2 function. But the fact that you can form this integral is because gamma dot is an L2 function. So it makes sense. Since gamma dot is an L2 function. So in fact, you can think of this as in the following way. There's a map, we'll call it L, from the space of L21 paths in the manifold to the Hilbert space of L2 functions in Rn. It simply sends gamma to gamma prime. And this is a continuous linear functional. And E of gamma is simply 1/2 the L2 norm of L of gamma. So it's a quadratic function on, it's the square of this linear, well, it's not quite linear, of this function L. It's a quadratic function. So anyway, the point I want to make is it's a smooth function. So E is a smooth C infinity function on this Hilbert manifold. Now we're interested, of course, in the critical point. So we're interested in the differential of E, which at any gamma will be a map from the tangent space to the manifold at gamma to the reals. And it's a bounded linear functional, continuous linear functional, because E is smooth, so it has a smooth derivative, has a continuous derivative. But this is a Hilbert space, so that implies there's a unique vector called the gradient of E at this point in this tangent space, such that the W12 inner product between E and any tangent vector lambda is equal to dE gamma on lambda. But we know what this is. By our usual computation, dE, you bring down a 2 and to cancel the 1/2, and you simply get dE at gamma on a tangent vector lambda is simply lambda dot gamma dot. The L2 inner product, so the integral from 0 to 1 of gamma dot t, lambda dot t. Again, these are both in L2, so you can take the L2 inner product. So that is also the gradient of E at gamma lambda with respect to W12. But I've already got a formula for the W12 norm. This is L of E of gamma, L of lambda. So I'm mixing two notations here, so I should pause and say a word about that. When I have a curve that's just simply given as, say, lambda of t, I'll write lambda dot of t for what I'm also calling L of gamma. So when I have more complicated expressions, so like the gradient of E and gamma, this is a path. So there's a variable t in here. It's a path in Rn. And I could take its derivative, which I would denote by putting a dot over this thing, but there's no good place to put a dot. So when I have a more complicated expression, I will switch notations and talk about the map L, which takes any path in M or any path in Euclidean space and simply differentiates it. So an L12 path, W12 path, you differentiate it, you'll get an L2 path. So here, the dot refers to differentiating the path in the t direction. Here, L refers to differentiating the path in the t direction. So we see that gamma dot, the L2 inner product of gamma dot with lambda dot, and the L2 inner product of L of the derivative of nabla with respect to t on lambda dot have the same L2 inner product, and that's true for all lambda in the tangent space. So this implies that the linear functional nabla E at gamma. So the linear functional that this gives is equal to gamma dot on the tangent space. So you might think, oh, well, that means that the derivative of the gradient is equal to gamma dot. Trouble is that's not true. And the reason is that this lies in the tangent space. So the derivative of so this is a path in the tangent space, so its derivative is also a path in the tangent space. Well, yeah. By definition, I don't want to say this. This is an L of omega 1, 2, M, P, Q, gamma. Because the definition of the gradient is a vector in the tangent space with a given inner product, namely the inner product that makes it dual, makes it adjoint to the differential. So by definition, this is in the tangent space, and when you apply L, you'll get a vector in L of the tangent space. Gamma dot is not in omega 1, 2, P, Q of gamma. I mean, it is true that the derivative, the gamma dot of T is in the tangent space at gamma. Oh no, that's not even true, sorry. So this is not true, and there's no reason to expect gamma dot of 0 to be 0, and no reason to expect gamma dot of 1 to be 0. So it doesn't satisfy any of the conditions. Right? You have a curved manifold, and well, here's a path in a curved manifold, and you take the derivative of the curve at a point, you do not get something in the tangent space to the manifold, because the manifold's curving. So while gamma dot and L of the gradient have the same inner product, they don't lie, this does not lie in the tangent space. So these are not equal. But what we do have is that if I compare L of the gradient at gamma and gamma dot, they have the same evaluation on L on the derivative of paths in the tangent space. That implies their difference. Let's call this now L of gamma. So L of gamma is then a vector in this space plus H of gamma, where H of gamma is in the L2 orthogonal space to L of omega 1, 2. Okay, so we have our Hilbert space here, L2. We have a closed linear subspace, L of omega 1, 2, gamma. And we have a vector gamma dot, or L of gamma, somewhere in this space. And we have the vector, the image of the gradient at gamma, which lies in the subspace. The difference of these two is a vector we're calling H of gamma, and it's perpendicular. So we have this equation, and H of gamma is perpendicular to the image of the tangent space under this continuous linear map. Okay, so that's where we are. Okay. So notice two things. One, that gamma is a critical point if and only if H gamma equals L gamma. So gamma is a critical point if and only if the derivative of gamma is perpendicular to this linear subspace. This is some L2 version of the well-known fact that a curve is a geodesic if and only if, so you have a curve of a submanifold. So this is compare. If M is a smoothly embedded submanifold in Euclidean space, and gamma is a curve in M, smooth curve, C2, then gamma is a geodesic if and only if gamma dot sorry, my picture before was misleading. What I said before is wrong. Gamma dot is in the tangent space. That's true. But it doesn't vanish at the endpoints. So the right picture, what I should have been saying is you have a smooth manifold, a curved manifold, and a path on it. Then gamma dot is in the tangent space. But the second derivative, gamma double dot, is not necessarily in the tangent space. It's just a vector in Rn. So this submanifold is sitting in Rn. But gamma is a geodesic if and only if gamma double dot at T is perpendicular to the tangent space at gamma of T of M. Because the covariant derivative of gamma dot is the perpendicular projection of gamma dot back to tangent space of M. And the covariant derivative will vanish if and only if this perpendicular projection vanishes, the second derivative, if and only if the second derivative is perpendicular to the tangent space. So this is some variant of that condition. Gamma is a critical point if and only if gamma dot is L2 perpendicular to the space of to the derivatives lambda dot. I mean, there's an integration by parts we're not quite seeing here. That's why it's a second derivative down here and a first derivative up here. Anyway, so that's the first thing to notice. I'll repeat it down here. Gamma is a critical point for E if and only if the derivative of gamma equals H of gamma, which is the perpendicular component, perpendicular to L of omega 1 to M P Q gamma. Okay, so that's the first thing to notice. And the second thing to notice is that the norm of the gradient, norm in its tangent space is equal to the norm of L of gamma minus H of gamma, the L2 norm of that difference. Because the gamma norm is just the L2 norm. So this is the L2 norm of the derivative. But the derivative of the gradient is this difference, and therefore the L2 norm of the derivative of the gradient is the L2 norm of this difference, and that's the gamma norm of E. Okay, so that's the second thing to notice. So once again, we see gamma is a critical point if and only if this norm vanishes, if and only if L gamma, the derivative of gamma, is perpendicular, is equal to H gamma. Okay. All right, how are we doing? That's the general introduction and setup. And now I actually have to do some computation. So I'm going to have to make a computation to show L gamma equals H gamma gives us more control on gamma, i.e. to prove, what we'll actually prove is that gamma is C1, and there's a formula for gamma prime that allows us to bootstrap. A recursive argument. Well, if if gamma is CK, you write down that formula for gamma prime, and you see that formula is CK, and therefore gamma is CK plus 1. And you just bootstrap all the way up to conclude that gamma is C infinity, though all you actually need to do is prove it's C2. Once it's C2, you can do the usual thing to show that lambda dot gamma dot dt is, you switch the derivative, you integrate by parts, it's the integral of lambda covariant derivative in the gamma dot direction of gamma dot dt. That argument that we've talked about before, integrating by parts to move the derivative from here to here, I guess is a minus sign. And now that's got to be true for any lambda in the tangent space. But if it's true for any lambda, that means that this thing actually has to vanish pointwise. Except possibly at the endpoints, because you can choose lambdas anyway. This sort of standard argument. Once you know this is continuous, you can't do this at the endpoints. But if this continuous second derivative vanishes everywhere except the endpoints, it vanishes at the endpoints, and that's the usual geodesic equation. So you end up proving the solution is, well, first you do C1 and then you bootstrap up and you get that the solution is C infinity, and then you can do the standard arguments to prove that this covariant derivative, in other words, gamma double dot, really is perpendicular in the naive sense to the tangent space to the manifold. Okay. So the whole point now is to use this equation, this L2 equation, to get more control over gamma. So what we know a priori is gamma is absolutely continuous, and its derivative is an L2 function. And the first step to get more control is to prove actually it's a C1 function. What you prove is that gamma dot is in W1, 2. So in fact, what you end up proving using this equation is that not only is gamma in W1, 2, but gamma dot, which a priori is just in L2, is itself in W1, 2. That implies gamma dot is continuous in particular and has an L2 derivative. That means gamma is C1 and has an L2 second derivative, and that's how you start the bootstrap operation. Okay, so that's what we're going to do. I have, how much time do I have? I have 11 minutes, which is fortunate because I don't think anyone could follow this argument as I present it, though I've written it down. I'll just say the key point in what you do. It's a funny mixture. So we've been talking about L of which is a nice closed subspace in L2. So far, we've talked a lot about that subspace, its orthogonal complements, that's how we got H and so on. Now we want to consider omega 1, 2, MPQ, gamma in L2. So maybe I should make the first one a map. I mean, it is an embedding, but it's a map. And here, I just mean the inclusion. So this is in some sense like the inclusion of W1, 2 into L2. If you have something that's got a first derivative in L2, in particular, it's in L2. But this is a funny subspace. It's not a closed subspace. And you have to look at its closure. And this is a very different space from this nice, the derivatives. The derivatives of things in here make a nice linear subspace in L2. The inclusion of these smoother paths, these W1, 2 paths, as L2 paths, this is like taking C infinity paths inside L2. You get a dense set, you don't get a closed set. You take the closure, and we think about perpendicular projection from the space of L2 paths to this closure. And you do some fancy footwork, which is all of it's fairly elementary footwork, estimates lead you to, let me see if I can pick out one estimate. You end up with this. If you take this orthogonal projection of H gamma, this turns out to be an W1, 2 path, and its derivative is equal to a smooth operator, smooth projection on gamma of t acting on H of gamma of t. So here Q is a map from the manifold into linear maps from Rn to Rn that sends a point P in the manifold. It's just the orthogonal projection to this subspace, tangent space at P of N. So you can apply this projection operator at gamma of T to H of T. Well, this is in L2, and this turns out to be in L2. So you can take products, if you will, of things in L2, and you get something back in L2. Okay, so pi sigma H. See, this is funny. H was perpendicular to the derivatives of tangent vectors. And here I'm projecting H not onto the space of derivatives, but onto the closure of space of paths. And I get a nice function. Anyway, so this is an L2, is a W12 path. But now let's invoke our equation. If we have a critical point, then H is in fact L, and thus pi gamma H gamma is pi gamma of L gamma, but L gamma is already, so this is L gamma. So we see that L of gamma, which of course is gamma dot, is W12, and we get that gamma is a C1 path. And we also have a formula for it. So this is L of gamma. So we have the second, well, here's a formula. L of gamma, gamma dot now. Anyway, so now, and you can use this equation to bootstrap. Okay, and get gamma C infinity. All right. Well, I wrote out more or less all the details of this argument in the notes that I'll post as soon as I read over them and try to get some typos out. I don't really have time to do it, and it's more arguments along the same lines to show condition C. You use the same basic result, that L of this projection of H of sigma is given by Q of gamma T H, sorry, gamma H gamma of T. So again, you use, there's a minus sign, again, you use this basic equation, do a little fairly elementary or, fairly elementary manipulations with norms to show if you have a sequence gamma n with bounded energy for all n. So that's the statement that E is bounded. And with the gradients, the norm of the gradient going to 0, in fact, gamma n forms a Cauchy sequence, or you can pass to a subsequence. It's a Cauchy sequence in W12IR. This is a Hilbert space, So these curves converge at least to something in W12IR in the W12. They converge W12. But omega 12 PQ is a closed subset. So that means that gamma is in fact a path in M from P to Q. Well, on the other hand, the gradient of E at a curve C norm and the C inner product is a continuous function. So gamma and gamma, the norms at gamma n go to 0, implies the norm of E and the limit is 0, i.e. we've constructed a critical point. In the closure of the sequence. Okay, so that's condition C. Once again, you have to do some elementary manipulations with the norms, but the key result is this formula for the derivative of the projection of H sigma onto the set of paths, the W12 paths inside L2, given by a formula like this, with Q being a smooth operator on the manifold. All right, well, that uses up my time. And I will start with Bott periodicity next week. Questions? And as I say, I've written out much more detail in the manipulations with the norms and so on, these technical results that I only gave the briefest introduction to at the end. So what I hope you take away is what the space we're working with is, what sort of paths we're thinking about. They're paths where the energy functional is a smooth functional, and then we have to use this equation, which is the analog of the second derivative equation for the covariant derivative, the equation that says the derivative of gamma is perpendicular to this space of paths, perpendicular to the derivatives of paths in the tangent space. So we use that equation, and then we manipulate in the way you tend to do in these arguments to build up, in the first case, a little more smoothness, in the second case, to get control on the norms of the sequence to prove the sequence of gamma n minus gamma n to prove it's a Cauchy sequence. All right, so any questions? Well, things will get easier when I go back to Bott periodicity. There's none of this delicate analysis arguments with various norms. Just have nice pictures coming. So even if you've gotten lost in these fairly technical arguments or discussions of how this goes, Bott periodicity will be easier. All right. If there are no questions, I'll see you next week. So long.